मेरे प्यारे बच्चों, इफ यू लाइक द वीडियोस चैनल को सब्सक्राइब करो और बेल आइकन बोले तो घंटी बजाना मत भूलना.
Okay students, let us discuss a very simple problem from mechanics today. Okay, so I'll take up this problem. We'll try to practically see what the issues are. We'll try to practically see how things work, and after that we will try to solve that with basic techniques that we have learnt in mechanics. For the understanding of this problem, for the discussion of this problem, we need basic understanding of few topics: Newton's laws of motion, friction and rigid body dynamics. So I'll get started here. Okay, see, we have this inclined plane over here with us, and what I will do is I'll put this body, which is essentially a cuboid, as you can see. This is a cuboid. So I'll put this body on this inclined plane and we'll see for ourselves what exactly happens. Okay, we'll see for ourselves in reality what exactly happens, and then we will analyze all this using a board, using a marker, basically in an analytical manner. Okay, so I'm putting this body over here on the inclined plane. So at this point of time, what we see is, if you look at it carefully, this body, I'm putting my finger here so that you can see what is happening exactly. Okay, so this body is very slowly going down. It is slowly and slowly slipping down. So what has happened is, I actually adjusted the angle of inclination for this inclined plane in such a way that this angle of plane with the horizontal plane is actually equal to the critical angle at which the slipping on the inclined plane actually starts. That is what I have done. So I adjusted the whole plane accordingly. So the whole thing is slipping so slowly, if I don't put my finger over here, now it is gaining momentum. Now it is gaining momentum and it is going down fast. But initially, if I don't put my finger over here, we won't be probably able to see the slipping process. So that is what I have done. So this is one possibility. When we put the block, the cuboid, on an inclined plane, this is one possibility. It actually slowly slips down, and if I increase the angle, maybe the rate with which it slips, it becomes faster. Okay, what are other possibilities? Let us try to think about that also. Well, if I, let's say, decrease this angle substantially, I'll adjust this accordingly. So if I decrease this angle substantially, what happens is, if I place this cuboid on the inclined plane, it simply sits over here. It is not going anywhere. It is not rotating. It is not slipping. It is simply just there. Okay. Now let us call this case A. The case which just I demonstrated just before that, I will call that case B. So this is case A, the previous one was case B. Okay. Now I'll again increase the angle and show you something else. Now consider this case. See, if I put this object like this, again it is just about to slip, but almost not slipping, almost at rest. Okay. If you notice carefully, this side over here, this side, okay, let us call this side X, the side with maximum length, let us call this X. So this side X is actually pretty large. If you look at all the dimensions, let us say this is X, this is Y, okay, and this is Z for the time being, X, Y and Z. So what is happening here is, X is comparable to Y, and in this scenario, you see, the body is either just about to slip or not slipping, but at the same time it is not toppling also, it is not rotating. Okay, but if I just change the orientation slightly, you see, magic happens. If I put it like this, now the smaller dimension, Z dimension, that dimension is touching the inclined plane. Okay, and the other dimension Y is perpendicular to the plane. Now what happens, if I leave it, what happens? It does not slip, it topples. It does not slip, it topples. Okay, we will call this case C. In this case, what we did, the smaller dimension of the cuboid, z dimension, I have kept that dimension touching the inclined plane. And when I do that, what happens is this body topples. Okay, so this is what we saw experimentally, this is what we saw experimentally, and we will try to solve this using analytical methods that we have learnt in Newton's laws of motion, friction, rigid body dynamics, and essentially basic mechanics. So, okay, so let's get started with that. Okay guys, so I demonstrated that problem experimentally, and now what we will do is we'll use basic mechanics that we have studied to analyze that problem analytically, to basically understand in what conditions, in what situations, you know, the case A or case B or case C will essentially arise. For the understanding of this problem, as I said earlier, we will need basic, you know, understanding of laws of motion, Newton's laws of motion, basic understanding of concept of friction, and basic rigid body dynamics, essentially the concept of torque and everything. Okay, so if we know that basic thing, we are good to go. Okay, so as I said, when I put this cuboid on top of the inclined plane, these three possibilities arise. These three possibilities arise. The first thing that we saw was, you know, one possibility is the block simply stays on top of the inclined plane, it does not slip, it does not topple, you know. Second possibility was toppling does not take place, but the body actually slips down the inclined plane. And the third one was slipping was not taking place, but the body topples on the inclined plane. Okay, so I will analyze this systematically one by one. I am taking case A first. Okay, well, what I have done here already is I have drawn the inclined plane. Inclined plane is making an angle theta with the horizontal direction and all that. Okay, इसके ऊपर ये on top of that ये ब्लॉक रखा हुआ है. ब्लॉक के ऊपर हमने क्या किया है, वेट के जो कंपोनेंट्स हैं mg sin थीटा एंड mg cos थीटा, आई हैव ड्रॉन देम. स्टैंडर्ड है, parallel to the inclined plane, component of weight will be mg sin theta, perpendicular it will be mg cos theta. We always know that weight is going to act on the center of mass of the block. So this point here, center over here for the cuboid is nothing but the center of mass of the cuboid, because the block or cuboid that I am taking here, I am taking it to be uniform. Okay, so it has uniform mass distribution and everything, so the center of it is nothing but the center of mass. So weight acts on the center of mass only, that's why I have shown these two forces to be acting on point O. Okay, next thing is, see, because of this weight, the body will have a tendency to slip down the inclined plane. And what friction does? Friction always opposes the tendency for relative motion. Friction always opposes the tendency for relative slipping. So friction will act in the upward direction, as I have shown. Okay, friction has to act in the upward direction. There is one more force which I haven't drawn yet, that is the normal reaction. Okay, well, as far as the normal reaction is concerned, I am drawing the normal reaction acting on the block now. Let us say this is the normal reaction acting on the body, and I will explain a little later why I have not taken normal reaction to be passing through the center of mass, which we generally do. Okay, I'll explain that a little later. So what I have done here, I have taken normal reaction in such a way that maybe its perpendicular distance from the center of mass is x, and this perpendicular distance from the center of mass actually matters. This will affect our problem, this will affect our solution, and its value will affect these possibilities, which one of the three possibilities will actually arise. So let's get started. Okay, I'm trying to analyze case 1 where there is no slipping and no toppling, which means there is no translational motion, there is no rotational motion, which means there is a translational equilibrium as well as rotational equilibrium. Let us try to impose that on this problem. Okay, for translational equilibrium, what do we need? For translational equilibrium, we need to show that the total force on the body has to be 0. And that is what I am going to impose here. I will say, see, mg sine theta is a force parallel to the inclined plane in the downward direction. I will say this force will be balanced by friction, mg sine theta. Perpendicular direction to the inclined plane, mg cos theta will be balanced by normal reaction. Now this is nothing but the condition for translational equilibrium. Friction equals to mg sine theta, normal reaction equals to mg cos theta. Secondly, we have rotational equilibrium. For rotational equilibrium, what do we need? For rotational equilibrium, we need total torque about the center of mass to be equal to 0. Let us see which of the forces are creating a torque about the center of mass. Okay? Well, if I look at it, the forces creating torque about the center of mass are weight essentially, then we have normal reaction, then we have friction also. These are the forces. But out of these forces, you see, mg cannot create any torque about center of mass. Why? Because mg is acting on the center of mass itself. So we understand, we know how to calculate torque of a force about an axis, about a point. If we use those basic understandings, this torque has to be 0. So we are left with only normal reaction and friction. As far as friction is concerned, you see, perpendicular distance of friction, force of friction, or the line of action of force of friction is like at a distance h by 2 from the inclined plane, and therefore the torque because of friction has to be friction F into h by 2. Okay. Also, please notice that friction, if given a chance, will try to rotate this block in a counterclockwise sense. About the center of mass, the rotation tendency will be like this, and therefore I am putting a positive sign over here. I will take anti-clockwise, counterclockwise torque to be positive. Okay, I am left with normal reaction. Now see, normal reaction, perpendicular distance from the center of mass or center of mass axis will be x. So the torque because of that will be n into x, but I will take that with a negative sign because of the normal reaction. You can see the torque will be in the clockwise sense. Can anti-clockwise positive, clockwise negative, total value has to be equal to 0. Okay. Well, this simply implies that nx is equal to f into h by 2. Yeah, n has to be equal to mg sine, n has to be equal to mg cos theta. Just do that. This is mg cos theta into x equals to mg sine theta into h by 2. So for this to happen, for this to be true, for this to happen, what do we conclude? We conclude that x has to be equal to h by 2 into tan theta. Okay, and this will be a possibility only when this x remains less than or equal to b by 2. Okay? As far as x is concerned, you can see it is the perpendicular distance of normal reaction from center of mass, this quantity, and this quantity, maximum possible value for that has to be b by 2. Okay, so this is what I did. X is equal to h by 2 tan theta. So simple सी बात है. We know the angle theta for the inclined plane. We know the value of h for this block. We can calculate this value easily. Then we will compare with b by 2. If this particular value satisfies this inequality, we are fine. So under these conditions, the block has translational equilibrium as well as rotational equilibrium. Okay. As far as this condition here is concerned, it is being satisfied as well as it is being satisfied. Okay. Having talked about case 1 in which there is no slipping, there is no toppling, we basically showed here that there has to be translational equilibrium, there has to be rotational equilibrium, and for both of them we have essentially figured out the conditions. Okay? In this case also I wish to basically point out on one more thing, which is, you see, friction value in this problem is mg sin theta. Okay? But we also should know कि friction has to be less than or equal to the maximum possible value available for friction. F has to be less than or equal to F max. So we will get another condition from here. This value has to be less than or equal to mu into mg cos theta. In other words, for this equilibrium to hold, tan theta must be less than or equal to how much? Mu. What was mu? Mu was the coefficient of friction between the block and the inclined plane. Okay? So if we know the numbers, what is mu, what is theta, what is a, what is b, we can check for ourselves whether tan theta is less than or equal to mu or not, whether x is less than or equal to b by 2, x is equal to x यानी कि h by 2 tan theta is less than equal to b by 2 or not. So just by looking at those numbers, we will be in a position to decide whether the block placed on inclined plane will slip down or not, whether it will be in case 1 position or not. Okay? Having done that, I will now analyze case B. In case B, what I have mentioned, there is no toppling but slipping. So the analysis for this part will not change, because I am saying there is no toppling, means there is no rotation, means there is rotational equilibrium, means there has to be torque about center of mass has to be equal to 0. So if I start with that condition, see, nothing changes over here, absolutely nothing changes over here. Okay? Ki mg cos theta into x has to be mg sin theta into h by 2. But on the other hand, you see, conditions here will change. In this situation, mg sin theta will not be balanced by friction. Actually, mg sin theta will exceed the maximum friction available. So I will change this discussion, I will change this analysis. This analysis will essentially remains the same. So let us now analyze case B properly. In case B, see, in case B, no toppling is there, but slipping is going to take place. So I want to analyze this situation, how this will happen, when this will happen. Okay? So because there is no no toppling, so condition for rotational equilibrium will essentially remain the same. So I don't have to do anything here. But on the slipping front, I have to see what is the relationship between friction and mg sin theta. See, in this case what will happen is mg sin theta, the component of weight in the downward direction, will not be balanced by friction. Friction will be insufficient to balance mg sin theta. In other words, mg sin theta will be greater than or equal to the maximum possible friction force between the two surfaces. Okay? We all know, we have studied so many times in friction, that maximum friction available between two surfaces is equal to coefficient of friction mu, static coefficient of friction, and the normal contact force between the two surfaces. Well, this block cannot move perpendicular to the inclined plane. This is moving only tangential to the inclined plane, if at all. So normal reaction has to be balanced by mg cos theta. So as far as normal reaction is concerned, it has to be equal to mg cos theta. So this is the maximum friction force available, and even this friction will not be sufficient to balance it. That's why the condition. So when I put it all, this becomes mg sin theta greater than or equal to mu mg cos theta. In other words, tan theta greater than or equal to essentially mu. Okay? Now this simple analysis essentially tells me the following. It tells me the theta minimum value for slipping. The theta minimum value for slipping. That value comes out to be simply tan inverse mu. This is what I have done with this analysis. Okay, for example, if mu is equal to, let's say, 1, okay, then tan inverse of mu is simply equal to tan inverse of mu is equal to 45 degrees. That becomes my theta minimum value for slipping, you know. So what do we make sense out of it? If I know the coefficient of friction, I will figure out the minimum angle required for the block to slip down the inclined plane. What I have done here, I have taken an example कि if mu is equal to 1, then this minimum angle happens to be 45 degrees. So if I put the block on the inclined plane, angle of inclination is less than 45 degrees, slipping will not happen. Angle is greater than 45 degrees, slipping will happen, the situation will rise. Okay. So I'll stop this analysis here now again, and now I'll go back to the third case, which is we will not have any slipping. We will assume right from the beginning that slipping is not taking place. Okay, we'll assume slipping is not taking place, and we will find out the condition for toppling to start. Okay guys, now let us start with the discussion for the third possibility, case C. Let us try to see, you know, whether we are able to get a condition for case C also, whether we'll be able to decide just by knowing the numbers, value of theta, value of mu, you know, value of h and b, whether using all this we can decide कि slipping नहीं होगा, toppling होगा. Can we decide that? Let us see. Okay, so this is essentially the case C which I am talking about. See, here also we have assumed there is no slipping. Because there is no slipping, it means mg sin theta will be balanced by friction. A normal reaction will balance mg cos theta, no big deal. We have to, on the other hand, consider the possibility for toppling carefully. Okay, so I will start the argument in a reverse manner. I will again say, let us start with a possibility where there is no toppling also taking place. Okay, let us assume there is no toppling again. वहीं से हम लोग जाकर के कंडीशन बनाएंगे, ठीक है. सो अगर टॉपलिंग नहीं है तो सेंटर ऑफ मास के अबाउट जो टॉर्क होगा वो एसेंशियली जीरो होगा. नो टॉपलिंग विल मीन सेंटर ऑफ मास के अबाउट टॉर्क जीरो होगा. बट देन वी नो total torque is equal to torque because of weight, torque because of normal reaction, and torque because of friction. Again we know weight is passing through the center of mass, there is no torque because of that. So the total torque is only because of normal reaction and friction. So till here the argument basically goes in the very same manner. Okay? Now torque because of normal reaction, as we calculated earlier also, is simply equal to n into x with a negative sign, क्योंकि वो clockwise सेंस में है. फ्रिक्शन की वजह से टॉर्क एंटी क्लॉकवाइज सेंस में है, इसलिए वैल्यू f इंटू एच बाई 2 हमने पहले से ही लिख दिया था. हमें पता है नॉर्मल रिएक्शन की वैल्यू कितनी है. नॉर्मल रिएक्शन की वैल्यू mg cos थीटा है, राइट. तो एज इट इज हमने पुट कर दिया n का वैल्यू. दिस mg cos थीटा इंटू x प्लस f value we have already calculated, mg sin theta into h by 2. So if the block is still not toppling, this condition has to be satisfied. But then I will argue the following. I will say value of x cannot go beyond b by 2. The dimension corresponding to this side, the dimension corresponding to this side of the cuboid is b only. Half of it is b by 2 only. See, if there is a toppling tendency, what happens is normal reaction keeps on getting, you know, distant and distant from the center of mass. But normal reaction has to be essentially acting on the block only. So this normal reaction vector I cannot draw beyond this corner point. ठीक है, it does not make sense at all. So value of x, maximum possible value of x will be essentially equal to b by 2. So if I put the value of x equals to b by 2, see this is what I get, mg into cos theta into b by 2 plus mg sin theta into h by 2. This is what I get. If I am saying कि value of x I have put maximum and still the body now is in equilibrium here, rotational equilibrium, so value of theta I will get from here will be the maximum possible value for which toppling will not start, rotation will not start. That means if I cross that angle, toppling will start. ठीक है, so simply by solving this part, what do I get? I get tan theta equals to b by h, and please notice this corresponds to the minimum value of theta for which the toppling will start. You can see it in two possible manners. Either you say this is the maximum angle theta for which toppling does not take place, or you say this is the minimum value angle for which toppling will just start. So this is basically corresponding to the critical case. So I can now conclude from here कि theta minimum for toppling will be equal to tan inverse b divided by h. Tan inverse b divided by h. Again, let's take some numbers because it helps us to compare things. If I say that b divided by h is equal to root 3, pay attention to this. I am taking b divided by h to be equals to root 3. What does it mean? It means the base is big, height is small. Base is big in comparison and height is small. For this cuboid, this dimension is huge in compared to the height. That is what it reflects. So in this scenario, what we will get? We will get theta minimum for toppling to be equals to 60 degrees. Because essentially क्या हो जाएगा, यहाँ पे root 3 आ जाएगा, है ना. tan 60 के लिए वैल्यू क्या होता है? root 3 होता है. तो ये एंगल कितना बन गया? 60 डिग्री हो गया. हमें क्या पता चल गया इससे? हमें ये पता चल गया कि अगर हम ये एंगल्स लेकर के चलते हैं, ये नंबर्स लेकर के चलते हैं, तो 60 डिग्री के पहले टॉपलिंग नहीं होगा. इसका पहला केस हमने सॉल्व करके क्या देखा था? हमने देखा था कि 45 डिग्री के पहले स्लिपिंग नहीं हो रहा था, 60 डिग्री के पहले टॉपलिंग नहीं हो रहा है. With these numbers, I can now actually very easily decide which case will essentially arise when we are given a problem. Okay, let me now conclude the whole discussion. Let me conclude the whole discussion. See, if theta is less than tan inverse mu and theta is less than tan inverse b by h in this problem, then case A arises. No slipping, no toppling. ठीक है? This is what it is. On the other hand, in this case there is no toppling, but there is slipping. This is what happens when you have theta which is less than tan inverse b by h, but theta is greater than tan inverse mu. This is what will happen essentially. Third case, if theta is less than tan inverse mu, but it is greater than tan inverse b by h, then what will happen? Essentially case C will arise. See, okay? So now I can conclude this particular problem by saying कि if I know the value of angle theta, this dimension b, this dimension h, coefficient of friction and all these things, okay, if I know all this, what I can do is I can calculate the minimum angle at which slipping will start. For example, in our problem, it came out to be 45 degrees. I can find out the minimum angle at which toppling will start. For our example, that value came out to be 60 degrees. Now suppose angle of inclination for our problem, the problem we are discussing, is let's say 30 degree only. So that angle is less than 45, less than 60, both of them. No toppling, no slipping. If the angle is let's say 50 degrees, slipping starts but toppling will not start. So what will happen? Body will slip but it will not topple. Let's say if the angle goes even beyond 60 degrees, let's say 65 degrees. So what will happen? Now toppling will also start. So the moment you put the block on the inclined plane, it will simply topple. Okay. So we saw that a very practical problem could be solved using basic ideas of mechanics, right? Thank you.
बच्चों आप अपने क्वेश्चंस एंड सजेशंस कमेंट्स में डाल सकते हो एंड वीडियोस को अपने दोस्तों में शेयर करो और लाइक और सब्सक्राइब करना मत भूलना।